Good day, student. And now we continue our lecture in physics. Today we talk about membrane transport and the physical basis of electrocardiography. Membrane transport, structure of biological membranes. A bioplast is an open system which continuously exchanges different substances with the environment. This exchange is affected by transport of substances across the surface membrane of the cell. The processes of substance transport ensure cell breathing, feeding, electric activity, and a host of other important functions. Studying the electric properties of biological tissue and the electric phenomena related to the cell's vital functions is impossible without studying the processes of substance transport across the membrane, which in turn requires a preliminary consideration of the cell's membrane structure. Cell membranes are superfine structures with a thickness of 6 to 10 nanometers. The membrane separates the cell content from the environment. The cell also has internal membranes which surround such intracellular structures as the mitochondria, the endoplasm, reticulum, the Golgi apparatus, lysosomes, and others. The plasma membrane ensures relative self-sufficiency and stability of the cell's chemical composition, and at the same time it affects and regulates substance transport from the environment into the cell and therefore to the environment. The plasma membrane also provides formation of contact between cells. The specialized plasma membrane of nerve cells plays a key role in transmission of nerve impulses. The plasma membranes of the epithelial cells of the gastrointestinal tract and kidneys take part in the processes of absorption and secretion. The main components of membranes are proteins and lipids. Membranes also contain a small amount of carbohydrates. Phospholipids comprise the main parts of membranes lipids. They consist of two parts. The head, which is polar and therefore has hydrophilic properties. The other part is tails, comprising the residuals of fatty acids. The tails are nonpolar and so they are hydrophobic. The structure and the functions of the membrane proteins are very different. It is they who determine the functional diversity and specialization of biological membranes. Look at the picture. You can see the main components of membranes. Currently, the majority of scientists accept the liquid mosaic model of the structure of biological membranes. According to this model, the key continuous part of the membrane is a double layer or bilayer of phospholipids in which the polar heads are directed out from the layer and come into contact with the water medium, and the tail, which are directed into the bilayer and linked by hydrophobic interaction. Over a certain temperature range, the phospholipid structures combine the properties of liquids and crystals. As liquids, they possess fluidity, but as crystals, they maintain order in the arrangement and orientation of molecules. Therefore, a phospholipid system can possess liquid crystalline properties. At a temperature drop below a certain critical value, a transition of phospholipid from the liquid crystalline state to gel occurs. At the temperature which is common for the cell, the phospholipid bilayer is in the liquid crystalline state. According to the liquid mosaic model, proteins do not cover the surface of the lipid bilayer completely, but is if flowed therein. The character of arrangement with and relation to lipids classifies membrane proteins into peripheral and integral proteins. Peripheral proteins are arranged on the outer or inner surface of the lipid layer and interact with the heads of phospholipids. Molecules of integral proteins have large hydrophobic sections. These sections are embodied within the lipid layer. Some integral proteins permeate the entire membrane. Integral proteins are connected with the membrane by hydrophobic interaction. Function membranes. First, structural function. The outer membranes of a cell separate its content from environment, determines the form of a cell. Sheets or covers of organoids divide contents of various regions of a cell, providing their different composition and accordingly different biochemical reaction of them. Second, protective function. If the cytoplasmic membrane protects contents of a cell from undesirable influences of environment, that membranes of organoids carry out similar function in relation to own contents. For example, membranes of lysosomes protect a cell from its lytic enzymes. Third, transport function. It is carried out due to presence of porous canals and proteins transmitting agents. Transport of substances of those structures is carried out selectively and depends on a structure of substance. Pores and canals have small diameter, less than 1 nanometer, are covered by proteins which polar groupings cooperate with substances penetrating into a pore, promotion, or on the contrary, hindering from their transmission. Hydrophobic groups cooperate with the lipids of a membrane. The permeability of membranes can vary in dependence on a cell state. Fourth, enzymatic function. The most part of enzymes of a cell is concentrated on membranes. These membranes organize a biochemical reaction, including multi-stage or multi-phasic or sequential. They provide strictly certain directivity of reaction due to the certain sequence in locating of enzymes. A vivid example is respiratory chains of mitochondria. Fifth, electrogenic function of membranes consists that the outer membrane of cell due to presence AT phase carriers of ion creates a different of concentration potassium, sodium, and chlorine between cytoplasm and intercellular medium, and a different permeability of a membrane for this and other ions results in appearance of a superfluous negative charge inside a cell. And hence to a potential difference between the intrinsic and outside sides of a membrane. ATPase adenosine triphosphatase, the common name of the proteins decomposing on ADP and phosphate. Energy releasing it is used for realization of endothermic reactions. The sixth, Edison's function. This property causes existence of multicellular organism. The Edison happens despite of presence of the same charge of cells. The basic mechanism of an Edison's mechanical interaction, engagement of actin part of membranes, and B, coagglutination of membranes at participation of organic salts of the calcium cooperating with the carboxylic group of proteins and phosphatic groups of lipids. And C, interaction of the proteins, coating membranes, formation of peptide bonds. Seventh, receptor function. On membranes, there are receptor proteins or complexes which accept influences from environment and accordingly vary metabolism of a cell. And eighth, antigenic function consists that on a cellular membrane there are peptide structures characteristic for cells of a given tissue of the given organism. These structures are entered of muscle of cells due to the presence exercise of a host defines of an organism is possible. And mechanism of substance transport across the membrane. Look at the picture. You can see kind of passive and active transport through membrane. First, simple diffusion from membrane. Second, diffusion through channels, 3 diffusion using carriers, 4th active transport. The mechanism of substance transport can be classified into 2 groups. And the first, passive transport of substances. It is named so because it does not demand cell energy input for transport of substances across the membrane. The mechanism of passive transport includes different kinds of diffusion. Ordinary diffusion, facilitated diffusion, electrodiffusion, osmosis, and filtration. And second, active transport of substances. This kind of transport involves cell energy input. Passive transport. Passive transport through the membranes is related to some kinds of diffusion. In the simplest understanding, diffusion is a transfer of a substance from a space with higher concentration of the substance to one with its lesser concentration. Ordinary or simple diffusion of uncharged particles is described by Fick equations. At ordinary diffusion, the direction of substance transfer is opposite to that of the substance concentration gradient. If the substance concentration in space depends only on one coordinate, for example, on coordinate x, then the Fick equation is, look at this expression, the first, where dm divided by dt is a rate of diffusion. Mass of the substances born in unit of time through the area S. dc divided by dx, oh, I'm sorry, this is x. Gradient of concentration. X is a distance between points in which concentration C observed. Diffusion coefficient, which depends by substance nature, density and viscosity of medium, temperature and other factors, and is measured in centimeter in square per second. If one introduced the notation, the phi is a capital phi, is a substance floor, more exactly the substance mass floor, and G is a substance floor density. Then the first Fick's equations can be written in the form this expression. Look. Direct, what's my, it's x. This x, not t, it's x. It's my fault. Sorry. Direct diffusion across the phospholipids bilayer. The number of substances which are capable of diffusing directly across the phospholipid bilayer is very limited. These are some gases and non-electrolytes which are soluble in lipids. Most substances that are transported across the membrane cannot diffuse across the phospholipid layer. Diffusion through pores. Diffusion of most substances across the membrane is affected through specialized membrane formations known as pores or channels. They are formed from integral proteins. Diffusion of water, some simple organic compounds and ions occur through the pores. It is typical for pore diffusion that the membrane permeability for a given molecule or ion depends on the channel and the molecule dimensions. For ions, transport also depends on the ion charge and the potential difference between the membrane sites. Facilitated or lightly diffusion. Facilitated diffusion is effected by means of so-called proteins carriers. At facilitated diffusion, the molecules of the transport substance from a complex compound with the molecule carriers. Facilitated diffusion is characterized by the following. First, permeability of membrane is significantly higher than diffusion of thick determined by the law. And the second, saturation, a stream of substance phi increases only up to achievement of some limiting value of a gradient of concentration. Third, high specificity, the certain substance carried only with a similar structure. Fourth, the expressed sensitivity to low concentration of inhibitors and activators of a carrier. Fifth, integrity with streams of ions through a membrane. Electrodiffusion is diffusion of charges, particles, namely ions. The phenomenon of electrodiffusion involves not only availability of an ion's concentration gradient in the medium, but also the presence of an electric field potential gradient. The electrodiffusion phenomena is described by the Nernst-Peake equation, which has a form this one, where U is a ion mobility. Z is an ion charge expressed by elementary charges. F is a Faraday constant, and phi is the electric field potential. And d phi divided by dx is a potential gradient modulus. Taking into account that ion mobility is equal to d divided by RT. R is a universal gas constant and T is absolute temperature. The Nernst-Planck's equation can be rewritten as this last expression, the last form, rewriting in this last form. Osmosis is a locomotion of a dissolvent from a range with a smaller concentration of solute in a range with a greater concentration. As a matter of fact, it is a diffusion of a dissolvent. This appearance is observed in the presence of semi-permeable membrane between specified areas. Electroosmosis is locomotion of a dissolvent in an electrical field if molecules of dissolvent are charged or owing to the osmosis accompanying locomotion of dissolved charged particles. Abnormal osmosis happens at presence both a concentration gradient and a condition for electroosmosis. If the electrical gradient interfaces with osmosis and locomotion of a dissolvent goes on an electrical gradient against concentration gradient. Negative abnormal osmosis is observed. If electrical gradient only reduces rate of transmission on a concentration gradient or even enlarges, it speaks about a positive abnormal osmosis. Filtration is a movement of water and solute molecules across the cell membrane due to hydrostatic pressure generated by the cardiovascular system. Depending on the size of the membrane pores, and solutes of a certain size may pass through it. And active transport. Active transport of substances across the membrane is related to the action of ion channels. The channels are formed by integral membrane proteins whose hydrophilic polar groups are directed inward the channel. Most channels have intrinsic selectivity, which is a capacity to let only certain ions pass. Sodium, potassium, calcium, and chlorine channels are known. Ion channel action is regulated by the cell. Due to conformational alteration of the proteins which form the walls of the channel, it can switch from the open state to the closed one and vice versa. One of the it is higher. Such transfer is impossible without cell energy input. Active transport of substances is often related to the action of so-called ion pumps. Look at the picture. You can see the sodium-potassium pump of plasma membranes. The calcium pumps of sarcoplasmic reticulum membranes and the proton pump of mitochondria and chloroplasts. Active transport includes transfer of different substances, for example, sugars across the membranes of intestine epithelium cells. We will consider the sodium-potassium pump. 3 sodium ions and 2 potassium ions are usually transported during one pump action cycle. Through under artificial conditions, this relation can be another one. Sodium and potassium ions are transported across the membrane by the complex integral proteins carry the hydrolyzer ATP, whose energy activities the sodium potassium pump. This proteins is known as the transportin ATPase or sodium and potassium ATPase. Ion transport is caused by conformational change in the protein carrier. Ion transport during sodium-potassium pump action results in an essential difference in sodium and potassium concentration in and beyond the cell. One distinguishes intercellular and extracellular concentration of some the ions, particularly chlorine ions. Such a difference in intracellular and extracellular concentration of ions with different charges yields a difference of potentials between the outer and inner surfaces of the plasma membrane. And biopotentials. In a state of rest, the cell's inner medium is charged negatively relative to its environment. The difference of potentials between the inner and outer sides of membrane is known as the membrane potential. And we can write down this expression. If a cell is in a state of rest, the membrane potential is known as resting potential, and we can write down phi r, the resting potential. The resting potential of different cells of various organisms can have different negative values in the range of about 50 to 100 millivolts. At present, the best model that describes the formation of the resting potential is a model which assumes that in the stationary state, the sum of flows of basic ions, potassium, sodium, and chlorine is equal to 0. And we can write down this condition look at here. Proceeding from this equation and using the Nernst-Planck equation, one obtains the Goldman-Hodgkin-Katz formula for the membrane resting potential. And this, look at this big expression, this one. It's a resting potential, phi r, is a membrane resting potential, and P K and the P with sodium and chlorine are the membrane permeability coefficient for potassium, sodium, and chlorine ions, respectively. potassium, sodium, and chlorine are active concentration of this in a square brackets. It's a concentration of potassium, of sodium, and of chlorine. In this formula, the membrane permeability for an ion is considered as the proportionality factor between the density of flow and these ions across the membrane, and the difference of concentration of these ions on both sides of the membrane. In the simplest model of ion diffusion across the membrane, the permeability of the membrane is equal to P. Look at this expression, where K, the small k, is the distribution factor of the particles of substance among the membrane and the environment, usually water. And lambda is membrane thickness. The permeability of a cell membrane for different kinds of ion is essentially different. If one takes membrane permeability for potassium as unit, then the following relation. Look at this relation. For potassium is its unit, and we can write this relation. This relation shows that potassium ions have a key role in forming of the resting potential. The process of action potential formation is related to a significant and non-simultaneous change of membrane permeability for sodium and potassium ions. First, after reaching the threshold value, the sodium channels open and the bulk of sodium ions pour into the cell. This causes depolarization and subsequent membrane potential reversion. Then the potassium channels open and the sodium channels closed. The bulk of potassium ions exit the cell. Then the sodium and potassium pumps activate to recover the sodium and potassium concentrations which are close to the initial ones. As a result, the membrane potential again becomes negative. Membrane's repolarization occurs. And we can see three phases. The first phase, a phase of depolarization, change of polarity of membrane potential differences. Look at this a small picture about cells. Outer and the inner environment of cells, and what happens in this situation, and the depolarization. And second phase, a phase of repolarization, reduction of amplitude potential of action, and restoration of polarity of membrane potential differences. And third phase, a phase of hyperpolarization, a value of module of membrane potential differences more than a stationary value of potential of rest. Duration, the form and the value of potential of action essentially differ for membranes of various cells. Action potential generation in a membrane section causes membrane potential changes and adjacent sections of the membrane. If these changes exceed the threshold value, this in turn causes action potential generation in this adjacent section. As a result, the action potential wave propagates across the membrane. In muscle cells, this process causes its concentration. In the nerve cells, action potential wave propagation across the membrane represents nerve's impulse transmission. And then I'll talk about electric dipole and the physical basis of electrocardiography. Talk about a basic characteristic of electric field. Electric field is a field generated by electric charges and performing their interaction. Electrostatic field is a field generated by fixed electric charges, the quantity of which does not change with the interval of time. Major characteristics of electric field. And the first, the fourth characteristic of electric field is called strength, tension, or intensity of electric field. E, with a letter E. In some point of the electric field, the intensity is equal to the ratio of the force affecting from the electric field on a charge Q placed in this point to the value of this charge. Q is a test charge, a unit of positive charge, positive. F is a force acting from the direction of field on the test charge located at the given point. E is a vector physical quantity being the force characteristic of the electric field. The dimension of strength, it is in Newton divided by Coulomb, or this voltage divided by mass. In a metric system C, the unit of intensity is volt per meter. The unit of the charge is a coulomb. Schematically, electric field is represented using strength line. These are force lines. Look at this picture. Force lines are lines tangents to which at each point of electric field coincides with the field vector at the point. And the force lines of electrostatic field are not closed. They start on the positive charges and are finished on the negative charges, or continue into infinity. This situation. The next major characteristic of electric field is potential difference or potential. The power characteristic of electric fields are called potential or potential different. The potential of electric field, phi, is a scalar quantity being the power characteristic of the electric field. In some point, the potential of the electric field is equal to the ratio of potential energy of a charge placed in the point to the value of this charge. WVP is a potential energy of test charges located at the given point of the field. The electrostatic field is a potential. That is why work executed field equals dimension of potential energy. Look at this expression. Where U is a difference of potential. It is named also tension or voltage. The tension or voltage. Where A is a work done when a unit electric charge is moved between 2 points having different electric potential. The C derived unit of electric potential difference is a volt. Geometric position of points having equal potential is called equipotential surface. Look at the picture. You can see equipotential surfaces. It's a blue line, this, around the charges, blue line, this. Correlation between characteristic of uniform field, where E is a constant. The intensity is connected with the potential by the ratio. This E is equal minus gradient potential. Phi is a different differential operator named a gradient and expressed through the partial derivative on coordinate. The partial derivatives. Look here. This gradient. It's a definition of gradient. Where I, G, and K are the vectors of unit length, odds, directed along coordinate axis or X or Y or Z accordingly. These components of the vector E along the specified coordinate axis are equal to this. It's X coordinate, Y, and Z. And we can write down this expression in the box. And this gradient we can rewrite using this sign of delta. D is a distance along direction E between points with the potential phi 1 and phi 2. Signed with minus in formula indicated that vector is directed towards decrease of potential. And we can write down this formula. This U divided by D. The direction of the vector of the potential gradient coincides with the direction of the fastest increase of the potential. Electric charges and the variable magnetic field generate the electric field. The intensity of the electric field created in some points by an isolated point charge Q is calculated by the formula. This one, look at this expression. Where at epsilon is a dielectric permittivity of medium, and epsilon 0 is the electric constant, and R is the distance from the point in which the intensity of the field is determined up to the point in which there is a charge. At the same time, the potential of the field in the given point is calculated by the formula. This one is phi. If the field is created by several charges, its characteristics are calculated from the principle of superposition of fields. The principle of superposition of fields. Look at the picture. According to this principle, the intensity of the electric field created in some points by several charges is equal to the vector sum of intensities of the field created in this point by each of charges, and the potential is equal to the scalar sum of potential created by each of charges. E and phi are the resulting intensity and the potential of the field created by charges. E1, E2, and etc. En are the intensities of fields created by each of the charges. Phi1, Phi2, etc. Phi n are the potential of fields created by each of the charges. Based on the principle of superposition of field, it's possible to calculate characteristic of field created by various system of charges. Electric dipole is an aggregate of 2-point charges plus Q and minus Q of the opposite sign equal by quantity and placed at the same distance d from one another, which is called dipole arm. The characteristic of dipole, electric moment, the P, is a capital letter P. P is a vector directed from the negative to the positive and with the amount that is equal to the product of charges and the distance between them. The dipole generates electric field which differ from field of dot charges, direction of the force line. They begin on the positive charge and are finished on the negative charge. Potential drop is a delta phi between two field points equidistant from the current dipole is equal to, look at this expression, so last. In other words, potential drop between two field points equidistant from current dipole and electroconductive homogeneous medium is proportional to projection of dipole moment onto the straight line which connect these points. Electrography. All live tissue source of electrical potential named is biopotentials. So electrography is a general name of all biopotential registering method that used with research and diagnostic purposes. Electroencephalography is examinations of electrical activity of brain. Electromyography is the examination of electrical activity of muscles. Electrogastrography, examination of electrical activity of digestive tract, first of all, stomach. Electrocolography is an examination of electrical activity of eyes, where oculomotor muscles are main source of signal. Most used method in everyday doctor's work is electrocardiography. The ECG records the electrical activity of the heart. This activity reflects the action of the cardiac muscles as it depolarizes and repolarizes during the cardiac cycle. The ECG represents the temporal and spatial summation of the action potential of the myocardial fibers, typically measured with body surface electrodes. ECGs are used to diagnose arrhythmias, abnormal electrolyte levels, and conduction abnormalities. They are also used for screening and therapy, guidance for heart disease, as well as a cardiac gating for imaging. In order to get an electrical signal from the body, suitable electrode amplification and appropriate display are required. Some cardiac cells generate action potential. When generated and under physiological conditions, the action potential propagates through the cardiac muscles. The temporal and spatial summation of monophasic action potential of myocardial fibers produced an electrical signal known as the ECG. Electrical activity of the heart. Electrical activity. The human body can be considered for purpose of an ECG, a large volume conductor. It is basically filled with a tissue surrounded by a conductive ionic fluid. You can imagine that the heart is suspended inside of the conductive medium. During the cardiac cycle, the heart contracts in response to action potential moving along the chambers of heart. As it moves, there will be one part of the cardiac tissue that is depolarized and another part that is at rest or polarized. This results in a charge separation of a dipole, which is illustrated in this picture. Look at this net dipole and these charges. The dipole caused current flow in the surrounding body fluids between the ends of the heart, resulting in a fluctuating electric field throughout the body. This is much like the electric field that would result, for example, if a common battery were suspended in a saltwater solution. The opposite poles of the battery would cause current flow in the surrounding fluids, creating an electric field that could be directed by electrodes placed in the solution. A similar electrical field around the heart can be detected using electrodes attached to the skin. The intensity of the voltage detected depends on the orientation of the electrodes with respect to that of the dipole ends. The amplitude of the signal is proportional to the mass of tissue involved in creating the dipole at any given time. Using electrodes on the surface of the skin to detect the voltage of the electrical field is what provides of electrocardiogram. Cells within the sinoatrial node are the primary pacemaker site within the heart. These cells are characterized as having no true resting potential, but instead generate a regular, spontaneous action potential. Unlike pacemaker action potential in the heart and most other cells that elicit action potential, the depolarizing current is carried primarily by relatively slow inward calcium currents instead by the potassium currents. There are in fact no fast sodium channels are operating in sinoatrial node cells. The sodium enters node cell through open calcium channels. This results in slower action potential in terms of how rapid they depolarize. Therefore, this pacemaker action potential sometimes referred to as a slow response action potential and sinoatrial nodal action potential are divided into three phases. Phase is a spontaneous depolarization that triggers the action potential once the membrane potential reach threshold between minus 40 millivolts and minus 30 millivolts. Phase 1 is the depolarization phase of the action potential. Look at the picture. This is followed by phase 4 repolarization. The cell is completely repolarization at about minus 60 millivolts. The cycle is spontaneous repeated. The change in membrane potential during the different phases are brought about by a change in the movement of ions or across the membrane through ion channels that open and are closed at a different time during the action potential. When a channel is open, there is increased electrical conductance of specific ions through that ion channel. Closure of ion channels causes ion conductance to decrease. As ions flow through open channels, they generate electrical currents that change the membrane potential. And William Einthoven was a Dutch physiologist who pioneered the ACG and won the Nobel Prize in Medicine in 1924 for this work. It was Dr. Willem Einthoven from the Netherlands who innovated the AKG for clinical use by refining the electrometer and delinear PQ RST waves. He used three lamb leads, which became known as Einthoven triangle. It is experimentally established that hot dipole during excitation generate action potential, which on a surface of human skin gives the lines of equal potential, equivalent lines. Look at this picture. Position of the dipole, moment of current dipole of hot and equipotential lines is shown. Through a hot dipole to lead the straight line A, B, and through the center of arm of dipole perpendicular 0, 0. Look at this picture, this 0, 0. Then on the part of positive pole of dipole, hot settle down positive and on the part of negative lines of identical potential. The line 0, 0 have zero potential. From the drawing is visible that if to apply electrodes on various points of surface of a body of the person, it is possible to determine the potential difference of these points. For the first time, theoretically proved points on the surface of human body from which it's possible to take potential of height have been offered by Einthoven. Dipole representation about height underline the theory of leads of Einthoven. The main postulate of Einthoven's theory are: first, the electric field of the heart is represented as electric field of current dipole, which is called the integral electric vector of heart. The second, P is in homogeneous isotropic conducting medium that is a tissue of organism. And the third, P permanently changes its direction and value. Now we will see some short video about ACG waveform. And just a moment.
The heart is essentially a muscle that contracts and pumps blood. It consists of specialized muscle cells called cardiac myocytes. The contraction of these cells is initiated by electrical impulses known as action potentials. Unlike skeletal muscles, which have to be stimulated by the nervous system, the heart generates its own electrical stimulation. In fact, a heart can keep on beating even when taken out of the body. The nervous system can make the heartbeats go faster or slower, but cannot generate them. The impulses start from a small group of myocytes called the pacemaker cells, which constitute the cardiac conduction system. These are modified myocytes that lose the ability to contract and become specialized for initiating and conducting action potentials. The SA node is the primary pacemaker of the heart. It initiates all heartbeats and controls heart rate. If the SA node is damaged, other parts of the conduction system may take over this role. The cells of the SA node fire spontaneously, generating action potentials that spread through the contractile myocytes of the atria. The myocytes are connected by gap junctions, which form channels that allow ions to flow from one cell to another. This enables electrical coupling of neighboring cells. An action potential in one cell triggers another action potential in its neighbor, and the signals propagate rapidly. The impulses reach the AV node, slow down a little to allow the atria to contract, then follow the conduction pathway and spread through the ventricular myocytes. Action potential generation and conduction are essential for all myocytes to act in synchrony. Pacemaker cells and contractile myocytes exhibit different forms of action potentials. Cells are polarized, meaning there is an electrical voltage across the cell membrane. In a resting cell, the membrane voltage, known as the resting membrane potential, is usually negative. This means the cell is more negative on the inside. At this resting state, there are concentration gradients of several ions across the cell membrane, more sodium and calcium outside the cell, and more potassium inside the cell. These gradients are maintained by several pumps that bring sodium and calcium out and potassium in. An action potential is essentially a brief reversal of electric polarity of the cell membrane and is produced by voltage-gated ion channels. These channels are passageways for ions in and out of the cell, and as their names suggest, are regulated by membrane voltage. They open at some values of membrane potential and close at others. When membrane voltage increases and becomes less negative, the cell is less polarized and is said to be depolarized. Reversely, when membrane potential becomes more negative, the cell is repolarized. For an action potential to be generated, the membrane voltage must depolarize to a critical value called the threshold. The pacemaker cells of the SA node spontaneously fire about 80 action potentials per minute, each of which sets off a heartbeat, resulting in an average heart rate of 80 beats per minute. Pacemaker cells do not have a true resting potential. The voltage starts at about negative 60 millivolts and spontaneously moves upward until it reaches the threshold of negative 40 millivolts. This is due to action of so-called funny currents, present only in pacemaker cells. Funny channels open when membrane voltage becomes lower than negative 40 millivolts and allows slow influx of sodium. The resulting depolarization is known as pacemaker potential. At threshold, calcium channels open, calcium ions flow into the cell, further depolarizing the membrane. This results in the rising phase of the action potential. At the peak of depolarization, potassium channels open, calcium channels inactivate, potassium ions leave the cell, and the voltage returns to negative 60 millivolts. This corresponds to the falling phase of the action potential. The original ionic gradients are restored thanks to several ionic pumps, and the cycle starts over. Electrical impulses from the SA node spread through the conduction system into the contractile myocytes. These myocytes have a different set of ion channels. In addition, their sarcoplasmic reticulum, the SR, stores a large amount of calcium. They also contain myofibrils. The contractile cells have a stable resting potential of negative 90 millivolts and depolarize only when stimulated, usually by a neighboring myocyte. When a cell is depolarized, it has more sodium and calcium inside the cell. These positive ions leak through the gap junctions to the adjacent cell and bring the membrane voltage of this cell up to the threshold of negative 70 millivolts. At threshold, fast sodium channels open, creating a rapid sodium influx and a sharp rise in voltage. This is the depolarizing phase. L-type or slow calcium channels also open at negative 40 millivolts, causing a slow but steady influx. As the action potential nears its peak, sodium channels close quickly, voltage-gated potassium channels open, and these result in a small decrease in membrane potential, known as early repolarization phase. The calcium channels, however, remain open, and the potassium efflux is eventually balanced by the calcium influx. This keeps the membrane potential relatively stable for about 200 milliseconds, resulting in the plateau phase, characteristic of cardiac action potentials. Calcium is crucial in coupling electrical excitation to physical muscle contraction. The influx of calcium from the extracellular fluid, however, is not enough to induce contraction. Instead, it triggers a much greater calcium release from the SR in a process known as calcium-induced calcium release. Calcium then sets off muscle contraction by the same sliding filament mechanism described for skeletal muscle. The contraction starts about halfway through the plateau phase and lasts till the end of this phase. As calcium channels slowly close, potassium efflux predominates and membrane voltage returns to its resting value. Calcium is actively transported out of the cell and also back to the SR. The sodium-potassium pump then restores the ionic balance across the membrane. Because of the plateau phase, cardiac muscle stays contracted longer than skeletal muscle. This is necessary for expulsion of blood from the heart chambers. The absolute refractory period is also much longer, 250 milliseconds compared to 1 millisecond in skeletal muscle. This long refractory period is to make sure the muscle has relaxed before it can respond to a new stimulus, and is essential in preventing summation and tetanus, which would stop the heart from beating. Thank you for watching. Please feel free to...
one short video.
The cardiac conduction system consists of the following components: the sinoatrial node, or SA node, located in the right atrium near the entrance of the superior vena cava. This is the natural